Okay, this chapter we're going to talk about something quite different called determinants. And there's a lot of theory involved that I'm not going to go into in detail. But determinants do have a great deal of importance, including in calculus and advanced calculus. And I can only give a small hint of why that's true. Now we know that linear algebra has geometrical interpretation. We can think of vectors as in a geometrical way. All right, so here are two vectors that we can represent. We also know that vectors can represent polynomials and so on. But consider these two vectors. These two vectors, if I draw the parallelogram, then they form a parallelogram like this. Now this parallelogram has an area. And the question is, how is the area of this parallelogram related to these two vectors? And we could write these two vectors as column vectors in R2. And it turns out that the area of this parallelogram is exactly equal to the determinant of this 2 by 2 matrix. Okay, so for instance, if I had one vector 1, 0, and another vector, say 1, 1, then I could form the matrix 1, 0, 1, 1, and take the determinant of that, and that would be the area of this parallelogram. Now it turns out that this is not just true for two vectors, but any number of vectors. If I have three vectors in three-dimensional space, and suppose, imagine another one coming up here. If you think about this, these form the edges of a box. I could form a parallelogram with the two base ones, and then I could form a box up here. Sorry about my bad drawing, but I hope you can see that you can form kind of a box. Think about the corner of a room, and you can create a box from that. Okay. All right, now it turns out that the volume of this box is equal to the determinant of the three vectors that form the corner. Okay, and you can actually generalize this to more than 3 dimensions, so it's a very amazing thing that you can do in multiple dimensions. And as I said, it's very useful in calculus. It's necessary in higher dimensional calculus. So sorry that we can't talk too much about the applications in this chapter. It's going to be more about how to compute determinants and some elementary properties. Okay, so we're going to relate determinants to a certain type of matrix called elementary matrices. Now, I think you've seen in this course that we keep going back to the same things and looking at them in different ways. And we had talked before about elementary row operations, and what we're going to talk about now is elementary matrices. Now, elementary matrices are related very closely to elementary row operations. Okay, now there are three types of elementary matrices. Here's one. This is very difficult to understand, this description, but what this description is saying is that you have an identity matrix. You start out with an identity matrix and choose two elements on the diagonal. And basically you switch these two rows. So if I switch these two rows, then this element of the diagonal goes up here, and this goes away, that becomes a 0, and this one goes down here, and that becomes a 1. Okay? And we'll see examples of that later on. So this elementary matrix you can think of as the identity matrix with two rows switched. And in this case, it's the K and L row that are switched. So this would be row K, this would be row L. Like I said, we'll see examples later on. Okay? Now, the second type of elementary matrix also looks like the identity matrix, except in one entry. We choose one entry, the entry on the II entry, and that 1 now becomes an alpha. We multiply that by a constant. Okay, so I want to kind of preview you to say that you know that one of the elementary row operations was switching two rows of a matrix. Now, this elementary matrix is obtained by taking the identity matrix and switching two rows of the identity matrix. One of the elementary row operations was multiplying a row of the matrix by alpha. Now, this elementary matrix is obtained by taking one row of the identity matrix, that is the ith row, and multiplying it by alpha. All right, now it similarly comes from, this last type is the most complicated type, similarly comes from elementary row operation. You take the identity matrix and you take alpha times one row and add it to another row. Okay, in this case you're taking, well, we'll see how that works out. I'm not sure which row is being added to which. I got to figure that out. Looks like you're taking the lth row, multiplying by alpha, and adding to the ith row. And what that's going to do is, if this is the lth row here, and this is the kth row, I'm sorry, I think I said that wrong. You're taking the lth row and adding it to the kth row. Right. So what that's going to do is, if this is the row L and you have the diagonal entry here, this is a 1. I'm multiplying that by alpha, I'm going to move a alpha up here. Okay. All right. So let's see how this plays out. We'll have some examples of these elementary matrices. All right. Now, here's some examples of elementary matrices. In this elementary matrix, this is the identity matrix with the first and third rows switched. Okay, imagine writing down an identity matrix, switching the first and third row, you'll end up with this matrix. And this is the first time of elementary row operation, and it was denoted this way. Okay, that's switching row 1 and row 3. This elementary row operation was the kind where you take one row and multiply by a constant. You can see that this matrix is the identity matrix. Just take row 2 and multiply it by 2. This last type was the type where you take a multiple of one row and add it to another row. Now what this does is it takes a multiple of row 3 and adds it to row 1. So it takes 2 times row 3 and adds it to row 1. All right, now this last elementary matrix corresponds to the third type of elementary row operation. Suppose I have an identity matrix that looks like this. And consider rows I and j. And suppose I take I, multiply by alpha, and add it to row j. What will the result look like? Well, in this I entry here, there's a 1. If I take row I and multiply by alpha and add it to row j, I'm going to get an alpha down here in the ji position. Okay. The identity matrix part will be the same. I'll have this additional alpha in the ji position. Okay, so you have 3 types of row matrices. This one, I was going to be more clear about it. This one looks like 1, and then there's a 0 here, and then there's a 0 here, and the rest are 1s, and the 1s here are flipped. That's the first one. Second one looks like this. It's got 1, and then in one place it has an alpha, and then it has 1s everywhere else. This one has, and there's 0s off the diagonal, and here there's 0s everywhere else. Okay, and this last one I have 1s on the diagonal everywhere, and then I have a single alpha off the diagonal, and everywhere else is a 0. Okay, so just emphasize again that these elementary matrices are produced by using elementary row operations and acting them on the identity matrix. All right, now why are these useful? Well, let's take an example. First of all, look at these elementary matrices. Here are examples of the elementary matrices we've just described. This is the first type where we switch rows 1 and 3, and you can verify that this matrix here is just the identity matrix with rows 1 and 3 switched. This one here is an elementary matrix of the second type where you've just multiplied the second row by constant 2. This one here is an elementary matrix of the third type where you've taken the third row, multiplied it by 2, and added it to the first row. Okay? So what's the big deal about these elementary matrices? Well, suppose we start out with A, some matrix A, and perform row operations on this matrix. For instance, suppose I want to switch row 1 and row 3. Okay? If I switch row 1 and row 3 of this matrix, I get this result. Now, look at this. Suppose I take this starting matrix A and I multiply it by this elementary matrix, which is obtained by switching row 1 and row 3 on the identity matrix. And you can work this out, and you'll find that you get the very same result. This result is the same as this result. Okay? All right, next, suppose I want to do another elementary row operation on this matrix here. Suppose I want to multiply the second row by 2. So this is the result of multiplying the second row of this matrix by 2. I could obtain the same result by using this elementary matrix, which is multiplying the second row of the identity matrix by 2, and multiplying that elementary matrix by the given matrix, and I get the very same result. Finally, this type of row operation, if I take 2 times the third row plus the first row, you'll end up with this result. I could have obtained that same result by using this elementary matrix and multiplying. Okay, so the result is summarized here. If A is an m by n matrix and B is a matrix of the same size that's obtained by a single row operation, then there's an elementary matrix of size m that will convert A to B by a matrix multiplication on the left. And basically what you do is, if you want to swap rows on your matrix A, then you use the elementary matrix that swaps rows of the identity. If you want to multiply a row by alpha, you use the elementary matrix that multiplies the ith row of the identity matrix by alpha. If I want to add a multiple of I times row, alpha times row I plus, and add that to j, I use the elementary matrix of the third type, where I perform that same operation on the identity matrix. And I'm going to skip the proof. I think you can see, if you work several examples, you'll see how this works. So I think that you should understand that all these long proofs come because people work with many examples and they see the patterns. So I'm just going to skip that proof. Okay, so let's prove some properties of elementary matrices. If E is an elementary matrix, then E is non-singular. Right? Now, there's a proof here. I'll just say the proof is that elementary matrices are row equivalent to the identity. As I mentioned, you get each elementary matrix by performing a row operation on the identity matrix. And we know that row equivalent matrices are that a matrix that's row equivalent to a non-singular matrix is also non-singular. So elementary matrices are row equivalent to the identity, therefore they're non-singular since the identity is non-singular. All right, now here's a very interesting theorem. Non-singular matrices are products of elementary matrices. Suppose I have any non-singular matrix. Then there exists elementary matrices such that A is equal to A1 through ET. Okay? Right. Now, the point is that if A is non-singular, then I can row reduce it to the identity. Now, we've just seen row reducing means multiplying A by a series of non-singular, of elementary matrices. So I can find elementary matrices E1, E2, up to E, let's say ET, and multiply that by A and get I. That's the same thing as saying that A row reduces to I. Now, these matrices E are non-singular, so they're invertible. And in fact, the inverse of an elementary row operation is itself an elementary row operation. So I can write A as equal, if I multiply both sides by E1 inverse, I'll get E1 inverse. And then if I multiply both sides by E2 inverse, I'll get E2 inverse, then multiply E3 inverse, E4 inverse, all the way up to ET inverse. So I can get A as the product of these inverse elementary matrices times I. But the inverse of an elementary matrix still corresponds to a row operation, so these are still elementary matrices. So any matrix at all can be written as the product of elementary matrices. Now, what makes this theorem less useful is that there's not just one way you can do it. You can do it many ways. There are many ways to reduce A to the identity matrix. So it's an interesting theorem, but not as useful as it could be. All right, so we'll stop there.